Alrighty. So, go in here. And so yeah, so like I said, we're just gonna work through one of Dr. Asadi's practice tests. So yeah, and I probably should have emailed this to him, but anyway, I'll just write the question down. You know, I can't share my screen and because I'm doing this on an iPad, so I can't quite do like what Dr. Asadi does and share his screen. But I will make sure that we understand the question, you know, before we start to answer it. So cool.
Sorry, Carl. The whole time, I don't know if it was because of me or what's going on, but I did not hear anything you said.
Oh no.
It was like reconnecting the whole time and like letting me barely in.
Really?
Yeah.
Can you hear me now?
Yeah, now it's fine. So I heard like the end of like not being able to share your screen, but I didn't hear anything.
Okay. Please let me know if that happens again. I don't know what. I didn't do anything. I don't know what happened. Now I just moved my stuff. But anyway, I'll make sure that you understand the question is all I was saying as we move forward, because I can't like show you the question from the test and then you know, like go back and forth like that. But I'll make sure that you know you understand the question. But I promise you, it's one of his tests. Here, right here next to me. I could turn on my camera and show you. I promise it's one of his old tests. So yeah, so let's get going here. And yeah, please let me know if I happen to cut out again or something like that. Okay, so so this is the situation. The first question, right? Question one, and remember that you know I can probably use that. You know, question one is going to typically be about what would it be? Chapter 19, I guess, in this case, and then just want these to be as straight as possible, but there's like a glare. I can't see the top of my screen to see if I'm making this straight. But okay, this will work. This will work. And so so this relates to chapter 19 majority, but there might be something in it. I can't remember actually, because it's, you know, his questions are pretty long. There may be something in there from because he tends to blend questions for this test, but actually for the first question, I think he always sticks with just chapter 19, but it's a second question that can always be a blend of kind of the things that are going on. Okay, so he says that you have these wires and and there's current going through them, right? So on the top, the current is going to the left. On the bottom, the current's going down. Now pay attention to this. This isn't a typo, okay? On the bottom, the current's also going to the left. Okay. So the top current's going to the left and the bottom current's going to the left, okay? The one on the side, on the left-hand side is going down, and the one on the right-hand side is going up, okay? So it's not, you need to notice these things for his test, right? Like you would think that, you know, it's a coil that's making a full, but it's not doing that, right? That's not what it's doing at all. Pay attention to that. Like, right, there's the current, right, is kind of, well, you can see what's going on. It's kind of like coming together right here, right? This is coming here. This is coming here. Not that you're going to have to like worry about junctions and things like this, but you just need to pay attention to the current direction is all I'm saying, okay? Make sure that you you know, and if you see something like this where you're like, oh wait, Dr. Sadi, did you make a mistake? And is this one supposed to be this way? No, this doesn't have to make sense, I guess, in terms of like the current, or like he could do it, you know, he could, you know, if he wanted to, you know, he could put this one down too, you know, he could make this the same as the one on the left. So, you know, he doesn't. This is what he has. So this is the question, but you know, it's a Dr. Asadi question, right? So we have a saying in the physics department, like, oh, it's a Dr. Asadi question. Like everybody knows what that means in the physics department. When someone says, oh, you have Dr. Asadi, like we all love him, but they know, you know, his tests, his questions are kind of like, where did that come from? So then there's this circular wire with a current as well in it. So this is a wire here as well, but there's a sorry about that. I thought I turned that off. This is a wire with you know, with current going in it. A little bit clearer. Okay, so you should already, like, even though you don't know the question yet, because you know that there's current, you know, in the middle wires, right? Current on the outer wires. What do you already know is gonna, I haven't given you the question, right? But what do you know always goes with a current? Like what always goes with the current? Always, always, always. Like what's paired with it? What did you learn in chapter 19? Yes, a magnetic field, right? So you should already be thinking, okay, I know these currents here. I know they have a magnetic field. Like you should like want to get the magnetic fields. Does that make sense? Like you should want to get them, want them. And even if you don't know the question. All right, so we can get them, but let's get a little. Let's make sure that we understand the total question. This is just the situation essentially, and then he gives us some givens. So this is right here. This is going to be what he's calling D. And you know, it's the same on both sides, right? But this is D right here. You know, obviously, you know, he points this out on his picture, but I hope, you know, we know that this is the radius. So, you know, if I go from so the distance from here, I think I was showing you all this in the review, right? The distance from here to here. What's another way I can write that distance? I showed you in the review, and that's what he does here. It's essentially, that is not letting me make that straight. But this is 2r, right? Because r and r, oops. Right, so the distance right there, right, is just 2, even though, right, it's just the two radiuses of the circle. That's actually the distance right there. Does that make sense? Okay. I hope that's clear. I don't know why it didn't make those as straight as I wanted to, but I wanted those to be a little straight. Okay, and then he tells us that D is equal to 10 centimeters, and he tells us that R is equal to 3 centimeters. Okay, and then the current, and he says the current is the same for all. So the magnitude of current is the same for all, for all, you know, even though, you know, there's different directions of current here, and there's 2 different, or essentially 4 wires here with current in them, or 5, I guess, total. they all have the same magnitude. Does that make sense? And it's this. So this is like, if you want to call this I1 and I2 and I3 and I4 and this one I5, they're all equal to each other. Does that make sense what I'm saying? I'm not gonna fit it in there. Darn it. Does that make sense what I'm saying though? So they all have the same magnitude. Okay, and it's this guy. Okay. So his first question here is, find the magnetic field at the center of the circle. Okay. And he does, I don't want to make this too confusing. He superimposes it on the picture, but he's giving us, if we need to do it, I'll move it over there. But for right now, just so this picture, we might have to draw another picture. I mean, it just is what it is. You should be comfortable drawing a ton of pictures in physics, but he just tells us like this way is Y, this way is X. Like he gives this directionality. And he wants to know what B is at the center right here. Does everyone understand the question? And so this is what he says. He says, find the magnetic field at the center of the circle. So what's another way to say what he doesn't say it in here, but if what's another way to say the magnet, like, yes, want the magnetic field at the center of the circle, and that's going to be what? Like what value have we've called it? We've given this value a name. We've used it in SI, we've used it in class. It's essentially a word that we use when we know there's right, because at the center here, well, I don't want to give too much away because the point of this is for you to think through this, and I don't want to hint too much at you. So if you don't know what I'm talking about, then let's kind of back up. And I want you to explain a little bit more to me, because again, if the worst thing that I could do right now, it's the worst thing I could do, is give you answers. I got the answer. Yeah, good job. This would be B net. Okay, all he says is find the magnetic field at the center of the circle. But let me ask you this. Great job, by the way. Why can we call this B net? Because not everyone knew that here. So let's make sure we understand, like, why the heck are we calling? He asked for the magnetic field. Why are we calling it B net? Why not call it B at the center of the circle? Like, why is it a more appropriate name to call it B net, I guess is what I'm saying. Let me ask you this. When you're netting anything, you're usually netting multiple things, right? Not all the time. Good. Yes, I'm getting the answer. There it is. Great job. Great job. There's a magnetic, the answer I got in the chat was there's a magnetic field for every wire here plus the circle. So essentially, this is B net because we're going to have to add all the magnetic fields together at the center. It's not just because of the magnetic field, right? It sounds like he just wants the magnetic field direction of that hoop in the center, right? But he doesn't. He wants the magnetic field here in the center, but the magnetic field here in the center is going to be due to all these currents, including that hoop with the current going through it, right? So essentially, right, and I shouldn't have erased these at the beginning, but like, if this is I1 and this is I2, and this is I3 and this is I4, right? Then we're going to need here in the center, that means that we're going to need to have a B1 plus B2 plus B3 plus B4, and I forgot to write, right? There's also I5 because there's that current in the hoop in the center. I forgot to write that. So that means also B5. So we have to net all the magnetic fields together here to get the magnetic field in the center of this hoop. Does that make sense? Do you see why we need to think of it? Even though he's saying, like, find the magnetic field at the center, you should say, I need a net. Or in order to get that, it's not just looking at the hoop and looking at the current of the hoop. I need to look at the currents of everything there, because all those wires, because they all have current going through them, they're all going to contribute to the magnetic field at the center of that hoop. Great job, everyone. Great job. Remember, and I told you in SI and everything, he is going to have you do that. Remember, I told you he's going to have you net magnetic fields. Like, it's going to, so here we go, right? It's literally off the bat. Okay, so tell me how to do it. Now this comes to you. You understand the situation, right? And by the way, like I said yesterday during the review, that if you're taking the test on Tuesday, or that would be tomorrow, please ask us questions to make sure the question is clarified enough, because the last thing we want you doing is being not clear with things. That's why it took so long just explaining the question. But now I'm going to help you through this, but this is a review for you. If I just give you answers, it will not help you. So I just need you to help me work through this problem. Pretend like I don't know much about physics in a sense. I mean, I'll make sure we get the right answer here. I'm not going to, take my brain all the way out, but, explain, like, tell me what I need. We have a game plan, right? He wants, the only thing we're trying to solve right now is the magnetic field at the center of this hoop. And you gave me a game plan. You said, Carl, to get that, I'm going to need to net all these things together. So you know what you need to do, right? So now tell me how to do that mathematically. Okay, so let's start. Let's take a step back. I hear you, but how about, because like I said, I want you to, one of the greatest physics teachers ever, his name was Richard Feynman. He said, you learn it best when you teach it. So like I said, pretend like I don't know physics. If you told me there's a mu, I'd be like, what? I don't see any mu or anything on this picture right now. What are you talking about? Where did that, you see what I'm saying? I'm going to play a little silly like that, because I want you to, I want you to maximize your points on the test. Okay, so how do you do that? You write down everything, every little step. Don't leave it out. If you can prove an equation, prove it. Okay. So I like what you're saying, because I do understand physics, so I know what you're saying. I don't want to say that you're incorrect, my friend. That's great what you're saying. But explain it to me like I have no idea going on. Like, what equations do I use here? What do I do here? Like, and I'll tell you right now, please keep this in mind, even though I'm not supposed to know anything about physics right now. The magnetic fields are vectors, and that's all I'm going to hint you at. So before you try to dabble with any type of equation, you better do something else. That's all I'm going to say. Because you can't net these without the direction, right? These are essentially plus or minus, plus or minus, plus or, I'm trying to hint you somewhere right now. You can't do this without direction. So it doesn't matter what equation you give me. If you don't have a direction, you're not going to be able to use it. Do you see what I'm saying? Whoa. Very important. Is everyone following me? This is how you need to think. When you think, okay, magnetic fields are vectors. I know because these things are vectors, just like force and everything else, I needed to get like their directions because that was the only way to net them together, right? And especially, right, how do you know you don't need to use like Pythagorean theorem here? You just can't grab at a quick, right? Think of all the things we've talked about in class and in SI, right? There's a lot of different ways to net magnetic field. And this is why I covered it so much in SI, because I'm telling you, he was going to have you do this, and you got to know it very well. So I'm going to go back to pretending like I don't know anything about physics. Tell me what I need to do first. Yes. Find the directions, right? I need to find the directions of the vectors. How do I do that? Again, you got to pretend like I don't, you got to teach it to me, right? So, because you all know this, right? You're finished with physics, you all. You have a week left. You're done. You can do this. I promise you. You can do this. Lean on everything you've learned in physics in the past for this test, okay? I got to find the vectors. So how do I do that? How do I do that here? How do I find the vector direction? Good. We look at the current. Great job. And we use, right? What? We got to use something. We also got to use the axes, which is correct, right? We got to say, okay, this is, and when he does this, I'll give you the full thing. He doesn't do this, but he would if you asked. So like, again, this is a good example. If this is the coordinate system that he gives on the test and it's confusing, just say, Dr. Asadi, is Z pointed outward? And he'd be like, oh yeah. And he would like, you know, to us, we do this so much. Sometimes we leave out details because I'm telling you, we see them even though they're not even there. Like our brain puts them in there. So sometimes we forget to put them in there because our brain sees them there, even though they're not there. And so keep in mind, like this is the coordinate system you're dealing with, right? So up is positive y, down is negative y, to the right is positive x, to the left is negative x, pointed out is positive z, pointed in is negative z. Everyone cool with that? And again, if you need us to clarify this stuff on the test, please don't waste a second, just ask us, okay? We don't want that stuff slowing you down. So now that we have a good vector, thank you for pointing that out. Now that we have a good direction to work with here, I got to use what to get the directions? There's something, what do we call it? It starts with an R. Yeah, the right-hand rules, right? And so which right-hand rule do we use here? It's the one where we put what in what direction. Like what, we have current here, right? So we're going to use current to get the magnetic field direction, right? How do I do that here? How do I use current? And remember, these are 4 straight wires here. So if you're looking at your notes from SI, you should be looking, or from the review yesterday, you should be looking for the right-hand rule for magnetic field for straight wires. That's what you should be looking at right now. Until we labeled it yesterday. Is it fingers in the direction of current? For the straight wires? Or is it thumb direction in the thumb in the direction of current for the straight wires. Remember, for coils, right? Coils and is a little bit different than the straight wires. So you got to know all. That's why there's essentially, even though it's like, oh, there's only 2 right hand rules. I'm like, no, there's not. There's 4, because they are different. Even though they look the same, they're not. They're describing 2 different things, right? So here, our thumb needs to be in the direction of what? I want to know the right hand rules. What I want to know. All I'm looking for right now is what right hand rule to use. Remember, I don't know what's going on. Because if you start giving me direction, I'm going to ask you, how do you know that? So you're going to have to use the right hand rule to tell me. I just can't say, oh yeah, it's inward and outward. It's like, how do I know that? How do you know that? You didn't tell me how, you're just telling me direction. And me, even though I don't know anything about physics, I'm a critical thinker. I'm gonna, not just accept everything you give me. I'm gonna ask you some questions, and if you can give some validity to it, I'm gonna trust you. But if you can't, then I'm gonna look at you like, you don't know what you're talking about. You just threw out answers. Good. Thumb in the direction of current, and then what should my fingers be doing? It should be, yeah, naturally curl around the wire. Exactly. So for I1, you're going to put your thumb in this direction. Okay, I'm going to move I1 for a second. You're going to put your thumb in this direction, right? And when you do that, if it were me, if you want to know how I'm starting, my thumb is in the direction of that I just said, to the left of the screen. And I have my 4 fingers pointing up, and my palm is facing the screen right now. So my thumb is to the left, my 4 fingers, my thumb is perpendicular to my pointer finger, and my palm is facing the screen. I don't care what direction my palm is. I'm just telling you what my hand's doing right now, okay? I don't want you saying, oh, do I have to have my palm in a certain direction? No, I'm just telling you what my hand looks like right now. And then I'm going to keep my thumb pointed to the left, and then with my hand, since my fingers are pointed up, I'm going to naturally just want to curl my fingers around this wire. And so when I do that, right, I can see that my starting position is going to be the direction of the current in front of this wire. On top, it's going to go inward, right? In back, it's going to go down. And on the bottom, it's going to come outward. Now, we're only concerned with the magnetic field on the inside, which means we only care about one of these magnetic fields. Which magnetic field are we concerned with? The one at the top, the one at the one in front, the one on top, the one in the back, or the one on the bottom? Which magnetic field are we concerned with? Top, back, bottom, or front? So if you're not sure, remember, you want the magnetic field that's closest in orientation to the spot you're looking for. Good job, bottom, the bottom. Right, because the bottom one, right, in terms of this dot right here in the center, it's the closest in orientation to it. So that's going to be the direction you're most concerned with, right? This one right here, it's not in the center, it's in front. right? This is the bottom one is not only the one at the bottom of the wire, but it's also going to be representing the magnetic field at the center right here from the top current from I1. Okay, so make sure you understand that. So the bottom is the only one we're concerned with, right? Which is out. Whoops. All right, so that's B1, which means it's in the positive Z direction, right? All right. Now, what about I2? What direction is I2? Or what direction, I guess I should say. What direction, what magnetic field direction do we need for the center? Let me ask that better, because we shouldn't be going through step by step here every time. This is like a test. Consider this kind of like a practice test, right? You should be just taking this kind of, I'm helping you through it, but you should just be taking. So what direction for B2 do I need to use for that center point right here? Just give me that answer. So we can't work step by step through everyone. What should be B2 direction? Outward or inward, up, down, left, right? Okay. Going backwards? Okay. Does everyone agree? Is it back? Is it? So we gave me an answer a while ago, and he said that it was he said it was outward. So I got one outward and one back. Mindy, did you wanna? You don't have to. I was just, and you can say, you know what? I'm still trying to figure it out. That's fine too. That's fine too. So thumb should be pointed down, right? So your thumb should be pointed down for I2. Thumb should be pointed downward, which means your fingers are going to go in on this side, and they're going to do what? Come out over here, right? And so since this is closest in orientation to the spot we're looking for, we know that that's the magnetic field that we need to use. So it's going to be out. Does that make sense?
Could you do that again? My chat was in front of what?
Nope, absolutely. So we want to, I'll kind of show you what my hand's doing over here. So I'm going to put my thumb downward, right? And I'm going to start, my starting position is thumb downward with my fingers pointed to the left. Okay. And then I'm going to just, just like you were telling me, like naturally want to pick this wire up. So I can see that, first of all, this starting position, right? That's going to be the magnetic field in front. And then as I curl my fingers around, I'm going to have to curl my fingers towards the back and to the left and back, and then towards me on the right hand side. Do you see how I'm doing that there?
Yeah, I did it right. I just didn't label them right. So I see like you go changing the way like you're wrapping your fingers is kind of the way that you go writing how it moves, if that makes sense.
Yeah. And he came up with this great, what he does is he just puts his pencil on the wire, like right here, like the picture of the screen in front of you. He just lines his pencil up with the wire, and he just grabs his pencil, and then he looks at how he puts his thumb in the direction of whatever current needs to be, and then he grabs his pencil and he looks at what his hand's doing as he grabs around the pencil, and you can see it that way too. So if it's hard to see on the screen, like just grab your pencil and literally just like wrap your, make sure you're putting your thumb in the direction of current, right? And then just wrap your hand around your pencil, and you'll literally see every direction is what happens. Does that make sense? Does that help?
Yeah, it does.
Awesome. I got to remember that. That's a really good time. Again, it's all online, and he keeps reminding me. He didn't remind me today. See, I remembered. I listen and pay attention to you. You're probably like, that guy doesn't listen to anything I say. No, I do. And thank you. Yes, thank you. I appreciate you. Everyone does. I think everyone. Okay, so B2's out. Okay, and then what about I3? What magnetic field direction are we concerned with I3? So just the B for I3. Just B3. What would B3? What direction should I use for B3? Whoa. Right it close to the so the top, when we say top, because I know what you're saying right now, and it is correct. But what direction is the top going? So because top wouldn't really be a direct, like when I say top, I'm saying like the vector on the top of the wire, right? But the vector on the top of the wire was like pointing in or out, right? And that's the direction we want to use. Does that make sense? Because you're correct what you're saying. It is the top. You're right. It's the if I were to wrap my finger around this wire, you're right. Whatever direction is on top of this wire is the one I'm looking for, right? Good. Inward, right? It is the top magnetic field, but we can see that our fingers are pointed inward on the top as we go, again, line our pencil up with the wire, go to grab this pencil, right, with your finger in the direction of current. You see, as you need to go grab it, you actually kind of start in the position that you need to be going. So yes, it should be inward. Good job. And Mindy, if you have questions, please ask them, okay? Because no one's gonna mind. Trust me, everyone's here saying, no, this is tough stuff. Like I don't think there's a dumb question here. This is challenging. And if you're confused, like, I think everyone would appreciate questions, okay? So let's what about I4? What should be the magnetic field direction for I4? Or B4, I guess. What direction am I going to use for B4? B4. So it has space. So we said outward. Is it outward? So so for I4 is pointing up, right? So the magnetic field definitely can't be in the same plane as the current. So just do the same thing, like take your pencil, right? Line it up with I4 current, which is, pointed towards the top of your screen, right? And then just go to grab, right? Put your thumb in the direction of current, right? Make sure you're using your right hand too. I'm telling you, I'm not lying. From even because we have to take a full electrodynamics class, I would put X's on my left hand because you'll just be writing. I'm telling you, and you'll start using your left hand. You're going to get signs completely wrong. Okay, so make sure that you're using your right hand, and then go to grab your pencil. Right, thumb in the direction of current. Go to grab my pencil. Right, and so my starting position is right now. My thumb is pointed up, and my fingers pointing to the right. And as I curl my fingers around my pencil, on the right hand side, it's going to be going in. On the back, it's going to be going to the left. And on the left, it's going to be coming outward. You see that? Should be outward. And then and as you can see, remember, Dr. Asadi and I both warned everyone in this class that you will not be able to do these questions without the right hand rules. Now you see what we're saying, right? Look at this. We still haven't done any math, right? We're still doing right hand rules here because you got to do so many of them. And I promise you, these are not. There's a lot to this question that we have not got to. Let me say that. So, what direction is B5, which is the current for the hoop? Remember the current, right? I5 is the current for the hoop. What direction is going to be what's going to be the current or the magnetic field direction? B5 for I5. What direction?
Sorry, really quick question on B4. So when you're looking at it and I'm holding my pencil and like where I'm wrapping it, so like we'll say like outward is like towards me, but then from there, if I move, can I say like it's going to the right? You know what I'm saying? Like it's
like for the front. Is that what you said? Yes.
So that would be like your X direction.
Yes. For the front, it would be pointed to the right and in the positive X direction. That is correct. Yes.
Okay. All right. Thank you.
Absolutely. Great question. And then obviously you can follow that all the way around. Great question. Okay. What about B5? And FYI, it's not the same right hand rule that we've been using just now. It's close to it. It's just not the same one. Right? You can't you can put your fingers in direction of current and get the answer you need to, but you should use the appropriate one here. There's a right hand rule for a coil that you should be looking at now. So the right hand rule for a coil, if I use that one, what's the right hand rule for a coil to get the magnetic field if I know the current? It's no longer, my thumb doesn't go in the direction of current. What goes in the direction of current now? My fingers, right? Yeah, curl, great job. Curl fingers in the direction of current. And then remember, before you start to curl your fingers, make sure your thumb is perpendicular to your pointer finger, right? And then just follow the current, right? So curl your fingers here. Here, you should be curling your fingers clockwise, right? With your thumb perpendicular to your pointer finger. And which way does your thumb point when you curl your fingers? If you're keeping it perpendicular to your pointer as you're curling them. Don't curl your thumb, just your fingers. What direction is B5? So, and the way I have this, it makes this look three-dimensional. That's why I don't like this. Remember, it's just, you're looking at this two-dimensionally. But let's not forget that these distances exist. I'll do it like that, maybe. But so if I curl my fingers, right, I shouldn't be curling my fingers in the plane of the screen, right? Just like if there's a clock on the screen, right? And you want to curl your fingers in the direction the clock, the hands on the clock move. That's what you should be doing right now. That's the way your fingers should be curling, right? Your thumb can only be pointed in one direction if you need to curl your fingers in that direction. Literally, your anatomy won't allow you to do anything else. So if you're curling your fingers like that, your thumb ends up pointed. Don't change your direction of your thumb as you curl your fingers. If you change the direction of your thumb and it ends up, let's say you curl your fingers and it ends up pointing upward, that means you change the direction of your thumb. If you go to curl your fingers in the plane of this, maybe I should say this might really help actually, I just realized. If you go to curl your fingers in the plane here, right, you have to start with your thumb pointed inwards. How are you going to curl your fingers clockwise if your thumb's pointed out at you? Do you see what I'm saying? You have to start with your thumb pointed inward and your fingers pointed straight towards the top of the screen. Does that make sense? That should be your starting position. So thumb pointed towards the screen, fingers pointed towards the top of the screen, and then just curl your fingers. Your thumb shouldn't change direction. Your thumb should, as you curl your fingers, your thumb should stay pointed towards the center of the screen. If it's not, then you're moving your thumb as you're curling your fingers. Don't do that. Just like practice. That's why you got to practice. That's why Dr. Asadi says you got to practice this, because as easy as it sounds, just curl your fingers. If you curl your fingers and then also turn your thumb, which is so easy to do, you're going to end up pointing in the wrong direction. Okay. So here, which way does your thumb end up pointing? It has to be pointing that way when you curl your fingers. We says inward. So, okay, you're saying it's going to be pointed towards the back, and the one pointed towards the back, that's going to be inward, right? So we are you're saying the same thing just in a different way, right? And that's inward, and then it's also going to be like the negative z direction, right? So let's actually write that now, okay? Because that's very important that we do this, okay? So we want to know that B1, well, I'm doing things for you again. I can't do that. So you need to, right? You should notice something here about B2, B1, B2, B4, right? They're all essentially what? In terms of direction, that's all we're still looking at here. B1, B2, and B4, they're all what? All in the same direction, right? Does everyone agree with that? You see they're all B1, B2, and B4. You see they're all pointed outward, right? In the picture. Did my sound cut out? Hello? Can you guys hear me? Oh no. Oh, okay, good. I'm just now worried after you told me that this cut out. No worry. Sorry about that. Yes, please think. I'll be quiet. I am so sorry. I'm just like all paranoid. Yeah, so as you can see, and we can write them across the bottom. Again, I'm telling you, the more organized you are, not only does it help you, but it will get you points on Dr. Asadi's test. Okay, so it's not a bad idea to say, okay, well, I can see that, to off here to the side, to say, okay, B1, right, is going to be pointed outward. I can see that, right there. And then B2, right, that's also going to be what? Pointed outward. Okay. B3, right, that's pointed inward, right? B4, that's again pointed outward, right? The direction that we're using. And B5, right, is pointed inward. It's there in the center, right? So those are all our directions, right? Do you see what I'm saying? Whoa. That we just got, right? But they're nice and organized. Now we can see them. And you can, what I would encourage you to also do is say that this is this right here, right? This is, we say positive Z hat. Get in the habit of doing this for Dr. Asadi's test. Positive Z hat. Because do you know why we write hat here? Like why that's kind of like an important thing, like to Dr. Asadi, why he tells you like, don't just write white, like you gotta write hat. Oops, what the heck am I writing here? Because it's a vector. And what we're doing is to show direction. We multiply these vectors. It's a mathematical thing. We multiply these things by what we call the unit vector in order to show direction. But remember, the unit vector, it has the value of 1. So it never, right? It's just like multiplying by +1 or -1. So you never change the value, but it does have a value. Like I get a lot of students that are like, well, is that just a, this variable? No. It has a number. It's 1. And like, so like here, this would be, a vector with the magnitude of 1 in the positive Z direction. Do you see what I'm saying? That's what that hat represents. And the same thing for like a negative. This would be like -1, a value of -1. Okay. Or a value, I'm sorry, not -1, a value of 1 in the negative Z direction. Sorry. Saying things not correctly. Okay. So and again, so this is a nice thing because now, right, you can see some things. This is what I was saying. You can say, oh, I can see here that B1, right? B1, whoa. B2 and B4 are in the same direction, and I can see B3 and B5 are in the same direction. See that? That's a good thing, okay, to recognize that helps you do some things, right? Because if we know that, all these magnetic fields are coming from a current, and again, this is a Dr. Asadi test. You have to put a lot together, so please pay attention with what I'm saying right now because it's just not like gibberish. It's the logic to the problem right now. Okay, this is how you put it together. As you say, okay, all these wires, not all 3, all 5 of these wires have the same value of current, which means if they have the same value of current, at least for the straight wires, not the circular wire, but at least for the straight wires, that means they're all going to have the same magnitude. Okay? Because they're all going to have the same. Like I said, we're going to have to draw it. The reason why is because they're all going to have the same, right, distance, right, at the center, right? This one's going to have, R, this one's going to have R, this one's going to have, I'm not doing this properly. Right, this is going to be R, this is going to be, right, they all have the same distance. I'm trying to draw that perfectly. I can, I'm not, but you're all very intelligent people. You all know those are the same distances, right? They're all going to be the same distance here in the center. So they're all going to be measured in terms of the same distance towards the center. Remember, direction does not mean larger or smaller. It just means that's scalar values. For vectors, when we say negative and positive, that just means direction here, right? But their magnitudes are going to all be the same because they're all the place that we're looking at here in the center. They're all going to be the equal distance to the center, and they're all going to have the same current. Does everyone understand? Again, this is the logic. If you can't think the way that I'm thinking right now, the words that I'm saying right now, that's where you get stuck on the test, because this isn't just a math class. Okay, it sounds very mathy what I'm saying. They're like, Carl, you're talking about numbers right now. Yeah, but I'm talking about physics though. Because the physics is that I know that the magnetic fields go with the current. I know that the current determines the magnetic field strength. That's the physics. And so if I know all the currents are the same, I know all the magnetic field strengths are the same. That's not math. Do you see what I'm saying? It sounds mathy, but it's not at all. That's physics. Okay, and then I can apply that. I know the equations that go here, right? But I can, using my physics knowledge, have an idea of what I need to do here. Okay, because if you don't have that extra step, which is the physics, that's where the difficulty lies. But trust me, there's a saying in physics. It says the math is the easy part. Believe it or not, that's the saying in physics. It's physics. It's the saying is math is the easy part. The physics is the hard part. And they're right. Look at the math. You know the equations. The physics, to sit here and get these right-hand rules and know that the values are the same, to be able to put these things together, that's tough. So we know, and if you're not sure, again, you can see it in the equation. Oops. Right? We know that the equation for straight wires, this is just for the straight wires here. I'm not talking about the hoop right now. Is this equation. Okay, if you don't know this, please, you should know this. Okay, we went through it remember in the review, I labeled everything up for you for this reason, because I knew that's how you need it for the test. Okay. And so you can see if R is the same for everything, right? Then, and let me put the direction left side. If R is the same for everything, then and I is the same for everything else in there is a constant. That means the magnetic field is going to be the same. Do you see what I'm saying? That's very important to know. Okay. So you want to write. You want to essentially, we're out of room on the other page, so we're going to do it here. You want to write, we knew this was I1, I2, I3. Oh, wait. Probably should have labeled that I3. That would make things a little less complicated. It doesn't make it complicated. I know what I'm talking about. And then you want to write these down. So I1, right? And also don't, forget that we've already said that, these are in the pot. Well, we'll represent that. I'll show you how to represent that in the equation. So for B1, it should be mu times what? I what? Should I just write I there? Is that what Dr. Asadi wants to see, is just I there and just R there? Is that what he wants to see? Is this going to get you a lot of points or very little, and probably have him like add something to say, oh, you need this? Good. It needs to be labeled. Yes, absolutely. Right. And the nice thing, hopefully we're understanding this, when things are labeled, you don't need to put numbers in there because we know what those numbers are, right? You just got done telling us this. This tells us everything. We know this is I. You've told us everything about numbers that we need to know. Okay. So then when you go through and do stuff like this, since you've established it, but you have to establish it. If you don't write what we did over here, he's going to say, I1, what's I1? He'll ask that as well. So it's a two-step thing. You can't just, even though if it's labeled I1, that's all good and great. But if you don't tell him what I1 is, then he's going to look at that and say, what the heck is I1? See what I'm saying? So just make sure everything correlates with everything. Very important. And then we said that B1 is in the positive Z hat direction. And that's what we do here. We just write, we don't do the positive in terms of vectors, as you already know, is always like just is always just unsaid, right? And so that is the way we represent positive Z, okay? So what about B2? How should I write that equation? This I should be what? Remember, B2, right? These are all straight wires, so it's always going to be this general equation. Just make sure it's labeled up properly, right? So if this is B2, right, this better be I2. If it's something else, you've done something very wrong, okay? Because it has to be that. Just like, right, we're over here writing B2. Please know this. Please know this. Like this could also be what? B induced, right? And that would be what? I induced then, right? You see what I'm saying? Like it works. You can write this equation. The equation's just this. And you can write it in terms of however you need, right? It's Ampere's law. Right? So you label this up how you need. Is it B induced? Is it B1, B2, whatever? It can be whatever it needs to. Just, you can't keep it like this. You got to make sure you label these things in here and this thing, right? And make sure that you have some sort of vector, showing the direction. And then this is going to be what? 2 pi R2, right? So what's going to be B? Oh, what am I missing here? The unit vector, right? I gotta show the direction. You've got to do this stuff, okay? B3. I hope we make it through at least one question today. Because this has a whole nother part to it, this question. We haven't even begun to start this question yet. So this is going to be mu times what? Good. But then good. We know that right? Is B3 in the I think I labeled these wrong again. That's my bad. You're saying correct things. I have these labeled incorrectly. Is the issue. Yes, and then this should be negative Z hat, right? Because I3, right? And B3 is pointed in the negative Z2. We determined all this already, right? I don't need to go hash that up again. All right. And then B4 is going to be what? Good job. Good job. Good job. Good job. All right. So what we see here is that look, B2, B4, B1, they're all the same equation, right? I mean, yeah, they have I2, I3, I4, but we know that those are all equal to themselves, and those distances are all equal. So those things are all equal. Does that make sense? So, now what about the circle? I don't think I could fit it on there. The hoop. Good job. Ugh. So this thing doesn't want to. Good. So we know that for the magnetic field for a hoop, right, it's mu times I to R, right? And then this is, this also needs a direction. And this needs to be, 5, and R is, in this case, going to be right, the radius. We call that R, 5. And we know what that is. To it. Good. Negative Z hat. Right? Good job. All right. So what do we know here? We know that because of the signs that we have, right? We know that B1, B2, and B4, they're all going to be positive, right? They're all in the positive Z direction. We know that B3 and B5 are both in the negative Z direction, right? So this is going to give us our B net. So now, right, we can put those equations in that we just had. But before we do that, you should actually, we could kind of save some time, but I don't want to use too much. You might need to do an extra step to do this, and that's okay. But maybe we can see it now. If not, we'll do an extra step, and then we'll see if you can see it then. Based off what we just did here, and the hint would be on this page, right? What do you think is going to happen here? Think about, like, again, you can't just think about these in terms of numbers, because then you won't be able to kind of develop the thinking that we're using right now. Should be able to see something. Again, if you told me, right, we came to the conclusion that all 4 of these equations are the same number, right? They have to be. Good job. Some of them cancel, right? I mean, we can pick whichever one here. Let's, right, because look, we got 3 in the positive, right? B4, B2, B1, and 1 in the negative. That means this one's essentially going to go away. And let's just cancel out B4. Let's say it could be any one of these if you want to cancel, but don't cancel them all out, right? B3 and B4, they're going to cancel each other out. Do you see what I'm saying here? Does that make sense? Because they're the same value. This is why, this is the physics. This is not math logic we're talking about here. This is physics logic that we're using here. Can you feel it, that it's physics logic and not math logic? Because it's important that you can. Because if you just think this is a bunch of math we're doing in here, it's just not. So these 2 things are going to cancel themselves out, is what I'm saying. So we're left with this equation now. B1 plus B2 minus B5 is equal to B net. And what do we know? B1 and B2, they're what? They're essentially the same equation, right? Yeah. So we can represent that, right? If B1 and B2, B1 is equal to B2, right? Then we can say that, which is equal to this mu I R. They're all equal to that, where I is just going to be, remember, we also established what I was. I is 10 right? Make sure you write this stuff down and establish it on the test, or Dr. Sai is going to say, what's I? But if you have I written down, you say, okay, these two things are going to be equal to this, because it's not labeled, right, with like 1 or 2 or 3 or 4, and it doesn't need to be because it's a general equation. Sorry, my pen acting up here. So that's what we know. So essentially, right, if I'm adding B1 and B2 together, it's essentially going to be 2 times mu I, right? Maybe I should write it like this. Yeah, it was given in the givens. Like he told us this number. Remember, I told you he gave us I, he gave us D and R. So he all he gave us were those 3 top numbers. Those are the givens. That's it. That's it. And so it's going to be 2 times this mu 2 pi r, right? Everyone agree with that? And then minus what? Mu I5, because that's going to, right? Just, we got to make sure that stays labeled still. Times 2r5. Cool? Everyone see that? Awesome. And then these 2's will cancel. And that leaves us with this equation. So this is the final equation. So this is what B net is equal to. Cool. All right, and then you want to make sure you're going to have to, well, you should be able to kind of guesstimate, right? This the magnetic field from the hoop's going to be a little bit stronger, right, than the magnetic field from the. Actually, is it? Hold on a second. No, you should, right. Look at this equation here. Like, so let me ask you this. I really wanted to move forward to the next question, but do you know what R is here? Because we know what R5 is. That's the radius of the circle, but what's going to be R here? Good job. Good job. No, it has an answer, and we got it. No. I mean, I love all the answers that are coming in, but we can say more than just greater than R5. We got it. It's the distance divided by 2. Because remember, great job. Great job, right? We said, I mean, it's covered now. Let me write it over here. But, right, we know that this is D, right? Right? So we know this is D, right? And so what's the distance to the center? It's half D, right? If I'm trying to, right, it's going to be D over 2. Does that make sense? To the center for any of these, for I1, I2, I3, I4, this is going to be, and we know D is 10 centimeters. Does that make sense? So you know this number. You know what R is going to be, right? R in this equation not R5. R5 is the radius. Everyone following me here? It's just R we're establishing. R, right, is going to be equal to D over 2. So maybe we should more appropriately write this equation. That's why I took time to do this, because I wanted to make sure you knew this got in there. Right, so if R is D over 2, that means there's going to be a 2 up here from this, right? And then this D is going to go on the bottom. Does that make sense? Cool. And so that's what you should be using for your B net. All right, so let's move forward to the next part of this question, because we're not done with this question. So he wants, the next part of this question is he wants to know what happens if we, this picture here, if we have these, you know, the situation that we have, and then he wants to know if we took a wire and put it through the center of this hoop, okay, and it has a current going through it, okay, and it sits, there's a theta here, right? So it, to the surface, it sits at a, or I'm so sorry, not to the surface. What am I saying? Not to the surface. It sits at a trying to make sure I'm doing this right, because he does have it drawn 2 different ways. Yeah, let me, he gives a different picture for this. I'm trying to use this picture and I shouldn't. There's a reason why he drew a different picture. Now I see. All right, so the picture he draws is, he just looks at it from the side because it's a more appropriate picture is why. So, right, if we're same situation, right, we're just looking at this from the side. Yes, I can. And then he puts the wire through here. Current's going like that, and he says that this is the angle. So this is the theta. Okay, can you see it now? So remember, this is, since we're looking at it this way, we've kind of like swapped directions now. Now, again, this is, you know, if this is not clear, you just ask us questions, okay? But now positive Z is pointed upward because we've changed the orientation of how we're looking at this. Does that make sense? So that means, you know, negative Z. Does that make sense? He wants to know the force on this current. Oh, and I'm so sorry. I am so sorry. I completely forgot to point this out. We pointed out it a few times, and then it just wasn't the time to talk about it yet. And then I spaced it out. But because it was, I'm trying to get us through this question, at least one. Look at this equation. What do we know about this equation? And you can kind of tell by the situation, but you know that the magnetic field from the hoop is going to be larger than the magnetic field from any of those wires. Okay, just because of the distance, right, to the center. The hoop's a lot closer to the center than it is than the wires are. But you can do the if you're not sure, if you're like, oh, how do you figure that out? Then do the math, but you're going to need a magnetic field direction here in order to do this next part. Okay. And so because, I mean, if you know physics really well, you can say, okay, I know whatever thing is closest to the place I'm trying to find, that's going to have the strongest magnetic field of them all. So we know for the hoop that the magnetic field was pointed inward. So we also know that that's going to be the direction of B net. Does that make sense? But if you don't know, if you're like, Carl, I can't do what you just did, I'm telling you, put the numbers in here. When you put all the numbers in there, you're going to get a negative number. And that negative number is telling you it's in that means negative Z direction. Does that make sense? Because both of these are in the Z direction. So if you get a Z, oh, I forgot to put that. Gosh darn it. I am messing everything up. But make sure to put those hats in there too. It's like I'm trying to rush now. And now I'm leaving things out, which is, I'm glad I went back and did this. So make sure that you put the, this is Z hat, right? And then minus mu I 5. Oops. 2R5. Oops. Call this D. 2 up here. And then this is also Z hat. Now you don't make this negative Z hat because you brought the negative sign out here. Does that make sense? But you still want the Z hats in there, which is the point that I'm trying to make. Make sure that you understand that. So that's a completely correct equation for Dr. Asadi right there, with the Z hats in there and everything. Okay. Let me clear. This is 2. Okay. So now, and we know once we get this, either once you do the math, once you put the numbers in there, or you can, have that concept in your head of the wire with the current that's closest to the point that we're looking at is going to have the strongest field, then you know that B net is going to end up being inward. Okay, that's what I'm saying. So we know that B net is, in this case, this is current right here, but in this case, which way is B net going to be pointing? And he does, go back to write it because I was drawing a new picture, but he does give us theta, but that shouldn't be slowing you down right now. And he does give us the current. Right, I'm just asking you what direction B is going to be in here. So remember, we've switched direction. Positive Z is up, negative Z is down. Before, positive Z was out and negative Z was inward. Now it's up and down. It's the same picture, right? This is still the same exact, right? The current's going through it like this. This is still I1. This is still I2. This is still I2. Oops, I keep doing that. This is I4, right? This one. Is I5, right? So you can use that as some help. That's the direction of I5 here right now. Direction is magnetic field using your right hand rule. That's the direction of I5. What do you mean? How do you know which one's closest?
Sorry, it's just kind of noisy, but well, because we took the one that was like closest to the center of the circle, but if it's coming out of it, how do you know which one's the closest?
Well, we took the closest one because of concept, but it was because of mathematics. Once we added them together, we saw that the magnitude would be pointed inward. But which way would you want to think about orientation here? So at first, right, it looked like this. Right now, all I did was, it's the same exact thing. All I did was flip it on its side, right? So when you were solving it like this, right, you had the x and y and z like this, right? So this was positive x, this was negative x. This was positive y, this was negative y. This was positive z and negative z. Now, if I flip this on its side like this, what's going to happen is this positive z is going to come up like this, right? And end up pointing upward if I flip it on its, like lie it flat. Do you see what I'm saying? And if I lie it flat, that means like this is going to be the direction of positive y now. So now positive y, because of my orientation, right? Positive y is backward. You don't need these, but I'm giving them to you. You just need the negative and positive z's, but right, the x didn't change. All I did was flip it on its side. It's just the z and y who kind of like changed direction, right? The x didn't change direction at all. Right, I just kind of like twisted it around the z axis, right, and laid it flat essentially. Cool. Okay, so now, right, and here, right, we said the net magnetic field. I mean, you can use the concept, but really just you need to be thinking of it as the net, because after we add all the magnetic fields together, we see that that net magnetic field has a negative sign, which means it's pointing to the negative z direction. So here, right, inward was the negative z direction. That was the direction of v net. So if we do this orientation flip where now positive z is pointing up, which way should b net point? If b net is supposed to be in the negative z, and we know positive z is pointing up now, b net should be pointed in which direction? You can't change a vector's direction. So if it's pointed in the negative z, you can't flip it in the positive z, right? That's a big no-no. It shouldn't change direction. It should stay in the negative z direction. Do you see what I'm saying? That's why I'm trying to help you. So positive z is pointing up right now. Just look at the scale right now, or the coordinate system. We said positive z is up. We know that v net is in the negative z, right? That's what we got over here when we did our math. It's not something we made up. It's after we added all these magnetic fields together, we found out that this was a negative. We got a negative sign. And because all of these were in the z direction, right? All of these were in the z direction. We knew that that meant negative z, right? We knew that meant negative z. And so we know that b net's in the negative z direction. So now we need to use that answer, the b net answer, which b net is in the negative z, to finish this second part of the question. This is still the same question we're trying to answer. We have not moved on to a new question, right? So we need to use that magnetic field we just found from netting all the magnetic fields from all those answers and see what the force is going to be on this wire. Does that make sense? So the magnetic field we got as b net was pointed in the negative z, so it shouldn't change direction, right? even if we flip this thing on its side, it shouldn't change direction. So B net is in the negative Z, right? For our original picture, then that means it should also be in the negative Z here, which would be pointed downward. Because downward is the negative Z direction, right? See what I'm saying? Does that make sense? Awesome. But remember, I'm not going to be there tomorrow to give you that logic. Okay. So it's something that, you know, you really, 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 truly want to understand. And if not, please ask questions. Okay. So that's the direction of B net. What direction is FB going to be? No, remember, it can't share. Everything should be perpendicular, right? It can't share a plane. Right. Everything has to be perpendicular, right? We know that, like in this case, and remember, these are the things you got to be able to do. In this case, like I, right, has components. I want to do that. Well, I guess that's the only. Oh, maybe this color will work. I has components like this, right? But what do you know? That this component of I, it's not perpendicular to the B. So it's not going to have any, it's really just this I right here that's going to, you know, contribute somewhat to the B, which again, remember, this is pointed in the positive Y. This is in the Y direction right now. So this is essentially, it looks like it's in the X, but it's in the Y direction. And this is in the Z direction. Does that make sense? Or I'm sorry, I said this is in the Y. This is in the Z. Sorry about that. But it's kind of pointed back. And so there's going to be some Y component that's going to give that to you. Hope that wasn't confusing. You really don't have to be thinking this way. What you should be doing is the right-hand rule right now. I was just trying to give you some background, but the way you get the answer here is the right-hand rule. There's no math. You should know that. You should know that anything for this test, if you need a direction, the only way you're going to get it is with the right-hand rule. There's no math, right? Well, being net, you need, you know, you'll be able to get without a right-hand rule, but you couldn't get B net without using the right-hand rules for all those other magnetic fields. So some of them you can get the direction with mathematics, but you're going to need the right-hand rule somewhere the way. It's not going to be just pure mathematics you're going to be able to use. So your fingers should be doing what right now? They should be pointed in the direction of current. So point your fingers in the direction of current, right? And then point your palm downwards. So right now, right? You want your hand kind of pointed towards the top right corner, like your fingers pointed towards the top right corner of your of the screen. I can't really draw this because it's gonna look kind of, I won't be able to draw this. But you want your fingers pointed towards the top right part of your screen, and you want your palm facing down towards the bottom of your screen. Does that make sense? And make sure your thumb is perpendicular to your pointer finger. If you're doing all of that, which way is your... No, you shouldn't be getting towards I1. I don't know how you'd be doing that. There's no way. You're going to get one direction here. I promise you. So your fingers should be right? I can't really draw this, but right, they're all aligned in that way. Like you can't see my fingers because they're all stacked behind. Like if you were to look at my hand, the way that I have it pointed, you couldn't see you would only be able to see my pinky. The rest of my fingers are aligned behind it though. And it's pointed towards, like this is my finger direction. And my palm direction is faced downward. So, because again, this is kind of hard to do over the internet. It's way easier to do in person. But your thumb should be pointed, whoa, in the z in the negative z direction. This way. What's the direction your thumb should be pointing? That makes sense? Remember this direction right here that's back, right? Which that's the y direction. And then this direction right here, that's the z direction. So you can see that the current sits in the z and y plane, right? So you know that FB is going to be in the x because you know B net is already in the z. So you know I2 is going to be related to the y. So that means FB has to be in the x because everything has to be perpendicular. Does that make sense what I'm saying? This is the logic that you should be able to go through. Okay, if you're confused right now, you should be able to go through this logic and say, okay, well, I2 sits like that, right? And so it's sharing some of the y, which is pointed back, and it's sharing some of the z, which is pointed straight up. And since everything has to be perpendicular, I know the z component of I is contributed. So it's just the y component of I2 that's going to contribute, right? Or is the direction that I need to use here in terms of the force. And so if I is in the y, B is in the z, you know that FB has to be in the x. You know it because everything has to be perpendicular. Does that make sense what I'm saying? That's a concept. That's why he kept telling you, remember, V and B and VB and F, they all have to be perpendicular, right? He said that so many times over and over. And this is why, because it's just not like rubbish to like say in the middle of class. It's like super important to the logic if you're going to work through a problem that's complicated like this. Does that make sense what I'm saying? If not, please ask questions, okay? I don't mind explaining things. I keep explaining things because I'm not hearing from you. And so I feel like you don't understand. So I got to keep clearing things up. So I'm trying to clear things up. So ask questions if you're confused, because then I'll know how to clear things up because I'm kind of just going at random right now. But if there's something specific you're not understanding, ask it because I'm trying to hit on that spot. And obviously I'm not if you're still confused, but I want to answer that question that you may have. Okay. not hearing from you. If you're typing, go ahead and type, but let's continue to work here because this is still just the first question, right? So FB, we know the magnitude, right? So we know the direction. It's going to be in the negative x direction. That's what we know. We know that. Okay. And what do we know about the magnitude? Well, it's going to be this, right? But remember, you got to use this equation to solve for it. Okay. Oh, sorry, it's not. It's the current one. I wrote down the wrong one. That's for there we go. That's for the individual charge here. So just keep in mind here so that we can move forward. You have all these numbers, right? This B right here, let's label this up a little bit better. This B right here is going to be that I is going to be the I that we're using. And then L, and then this is going to be B net, and this is going to be sine 30. Okay, and the I he gave us, and the length he gave us. Yeah, sorry about that. I forgot to write that down. My bad. Cool. So the math is plug and chug, right? As you can see, it's the right-hand rules that get you a lot of the answers, right? Because you could put these numbers in here at the beginning, but you wouldn't have had a direction, right? You have to do the right-hand rule to get the direction. Okay. Oh. I was making sure we had everything written correctly here. We know it's in the negative x, right? So we need to represent that. Sorry about that. And then we can say sine 30. And then, we're right. We took care of the negative over here, but then you want to put that x hat in there. My bad. Get you full points on the test, right? So don't just write what I had. Make sure you put the hat in the, you got to represent the direction, and that's how we represent the direction, as you can see. Okay, so we have gone through the 2 hours. Okay, trying to solve this test, and trying to solve this first question. As you can see, Dr. Asadi nor I weren't joking when we said that this was going to be a very complicated test, right? And I'll be honest with you, like Dr. Asadi considers the question we just solved to be pretty easy. Not super easy, but it's definitely nowhere near some of the complicated questions I've seen him ask. The thing that you all have going for you right now is that because it's summer, he is very nice. Okay, so don't worry about the questions being too insane. All right, but it's going to be very close to this. And if this was tricky, then, make sure that you study a lot tonight. But anyway, the point I was trying to get to was I'm willing to hang out and do the next question if you want to, but I do have to take off at 7 because I do have another SI. And but if you want to hang out and you want to do the next question that I had planned, I'm willing to do that. And if that one goes fast, we might even make it to the third question and we might get through both of them. Does anyone want to do that, or do you want to go? It's up to you. I don't want to keep you. We're in your personal time now. I'm just volunteering my time for you. Okay, I'll stick around and do it. You know, it doesn't help to just post it, because I'm telling you, if that, like I said, that first question was easy one. So this next one is, you're not gonna like it. Okay, it's very tough, and I'm telling you, I don't think posting this question you would you would want to have the work. Let me say that, to make sure that you're doing it right, because you'll be like, am I doing this right? Okay, because this is like, remember, he always, the way Dr. Sadi writes his tests, is that he always starts with there's always a super easy question, that's always going to, for this test, that's the third question. So, and then he does like one like that's kind of medium, it's not too bad, and that's the one we just did. And then he gives you an extremely hard one. Okay, and that's what this is. Okay. So he says that, and I'm going to do my best to draw this well, okay? But again, I'm no artist. So you have this solenoid. And it's attached to a variable DC, not an AC circuit, but a variable DC circuit, which means it can kind of work like an AC circuit, but I control that. So there's a dial that you can turn up and turn down and things like this, but it's not, actively, doing it. Well, let me just leave it at that. So that's what that is. It's a variable DC. I don't want to add any more detail. I'm just going to confuse you. So that's what a variable DC does. Okay, and that's what this solenoid's hooked up to. All right, and then what he does is he says that we place this circular hoop, right, around the solenoid. And he wants to, so this is just a metal conducting hoop, okay? And he wants to know, that's as good as it's getting. What the current is, what the induced current is. Let me just write everything here. So he wants the magnetic field of the solenoid. He wants the induced EMF. He wants the induced current, like the values for them. And then also when he says the current value, that he also wants the direction of the current. So these are the questions, okay? That's everything. There's no second part to this or anything like that. It's just, that's the question. He wants to know the magnetic field for the solenoid, the induced EMF, the current, and the direction of current. All right, so the givens, he tells us the length of the solenoid. Okay, he tells us the number of turns of the solenoid. It's 500. Okay, he tells us the resistance. Because it's a circuit, right? So it's going to have some resistance, and that's going to be 4 ohms. And then the EMF of the battery here, this is gonna, hopefully you'll be able to, again, this is very tricky. Usually when students see this, they get a little nervous. Is equal to this. Okay, that's the value of it. And yes, that is a T in there for time, which means that EMF is a function of time equation. I probably should write it like this. It's not an induced EMF. It's not induced. That's the EMF of this battery. Okay, and that's what it's equal to. Probably want the solution, huh? Like, I don't even know what to do with these numbers that he's like, these kind of made sense, but then this came in and I don't even know where to, how do I deal with the function of time equation for the source? Because that equation is telling you something, right? He wants to know the induced EMF and the induced current and direction, which means you're going to need to know the change in flux, right? Is there any indication of changes in flux sitting in front of you right now? Yeah. Okay, so let's solve this problem, okay? It's tricky and tough. And one time I asked Dr. Asadi, I'm like, Dr. Asadi, why do you work with function of time equations so much? He's like, because I know the students are uncomfortable with them. Like, he knows that when you see something like that, you're like, I'm not too sure what to do with that. Like, I can see the numbers in it. I know what potential is. I know what a function of time equation is, but I don't know what the heck to do with that. Right. And trust me, I've been there too. I've looked at those equations. I know you're the feeling you're feeling. I've looked at those and go, what the heck does that mean? Okay. So let's start this off you know, appropriately or with things that you should kind of, you know, have an idea of here. And let me see here. Does he give us? Oh yeah, he does. Sorry, it's in the picture because I don't have it here. You do need current direction of the EMF. I just noticed that wasn't there. And I was like, he doesn't give it in the wording. It's actually on the picture. So I apologize about that. And so he's saying that the current, I just missed it in the detail, but he's saying that the current in the solenoid, because there is a current going through it, right? Because there's just an EMF right there. He's saying it's to the right in front and to the left and back. Okay, to the right in front. He didn't say it in the words, it's in the picture. So again, if these things aren't clear on the test, you need to just ask us, okay? Because we don't want that to be the point of confusion. We'll just tell you. If you're looking at the picture and saying, I don't know what this picture is telling me right here, just ask. And we'll say, this is what it's saying. Because that is not where this, we want you to be able to work on the problem, not trying to figure out how awful our picture is, okay? All right. So does everyone understand? The current is to the left and front. This is the current, not the induced current. Remember, the induced current is going to be in this wire. This is the current direction running through the solenoid, right? So the I solenoid, right, is in the front. It's to the right, and in the back, it's to the left. I don't know how to abbreviate left. So that's what I'm getting. Okay, so how do I do this? What should be the first thing I should be thinking about? Anytime we did this, and it has everything to do with the last question we just did, actually. Think about the way we started it. Think about the logic. If you forgot it, that's not good, because those logic things are the really important parts of these questions. How do you know that we should be looking for B? Good job. Like B of the solenoid, right? That's what you're talking about, right? Not B induced, right? Or are you talking about B induced? Did I just put words in your mouth? We shouldn't be looking for B induced at all right now. We should be looking for B of the solenoid. And if that wasn't what you were looking for or saying, that's okay. But then you might not be able to explain why then. Remember, if you see, the way we started the last problem was, if I have current going through a wire, what else do I have? What does that wire have? If it has current, it has what? Yes, it has a magnetic field. It has to. So we need the magnetic field for the solenoid here. And why do we need the direction of the magnetic field for the solenoid? Why do we need that? We're looking for, like, the question's asking you for like the induced I and the induced E. How are you going to get those if you don't know what? How does induction work? Do you remember how induction works? Let me ask you that. Let's start with that. How does induction work? Explain the process of induction to me. What do we always start with? Help you out. What do we always start with? We always got to have this process always starts with the what? No, I mean, charge is there, but that's not, again, everything we did in the review yesterday is super, as you see, I only focused on the stuff you're going to need for Dr. Asadi's test in the review yesterday. But man, if you do not know the stuff we talked about in the review yesterday, you need to for his test, okay? If you have notes from the review from yesterday, I would be looking at those right now. All the answers from today you could have found in the review. Do know that, because I know exactly the types of questions he asks. Good. What type of magnetic field? Is it just B? It's very specific. What do we call this? Yes, B original. You got to have, and remember, B original was just the magnetic field that's present. It's present. It's already there. Where it's coming from, I don't know. It could be coming from a solenoid, right? But you got to start with that. Cool. And then what do? We have that B original. What do we have to do to it? We have to add a what? What do we add to that magnetic field? Yeah, add a conductor. And when we do that, that gives us flux, right? Well, over here, well, not there. Well, there too, but we didn't talk about it. Over here, right? We have a conductor with flux. Because the the solenoid is providing the B original, right? So I didn't say there's a change in flux, but if there's a current going through the solenoid and there's a magnetic field for it, that means there's a magnetic field in the center of this hoop, right? So there's flux because the hoop is the conductor and it's the thing that's defining the area for the flux, right? Oops. And then what do? We change some sort of, there could be some sort of change in the area, some sort of change in the magnetic field, some sort of change in theta, right? We went through all those details in the review, right? But when that occurs, then you have what? A change in flux. And once you have that change in flux, what do you get? There's the first answer we need for this question. So this is telling you the things that you need to do in order to get this answer. This wasn't just a graph to say, oh, what a fun graph, Carl. Please just give us the math now. No, you're going to need this graph in your head to do the math. That was the point of this. It wasn't just a teaching tool. It's literally a problem solver tool. Okay. And so, look, we're being asked for E induced. I know in order to get E induced, I better know something. I better know what? The change in flux. There's no way to, right? In terms of what I have on the screen right now, I might not be able to find it besides that way, right? But after we have E induced, we know we can get I induced. So, if I know Ohm's law connects I and E, so that I might be able to also solve for E induced if I know I induced, but typically that's not the way it goes, right? Typically I got to solve for some sort of change in flux. That change in flux is going to get me this E induced, and that's exactly what Faraday's law is, right? That's what that equation is doing for you. And then once you have that I induced, which is the second question we're asked to find I induced and E induced in the system we're talking about. So this is kind of showing you the process you've got to go through in order to solve for this answer, right? You're going to need to get E. Well, first you're going to need to solve for some B original. That's what you should be looking at. And once you get some B original, you're going to be able to look at the change in flux, and you're going to be able to find out what the E induced is. Once you know what the E induced is, you'll be able to find the I induced because you know about Ohm's law, right? And then what do you know? You know that this I induced, because there's a current, we just call this B induced because that's the magnetic field that goes with this current. If that was I2, that would be B2. But since it's I induced, it's B induced, right? And then we know when flux is increasing, right, that B original and B induced are in opposite direction. I'm just writing an abbreviated version here. When flux is decreasing, we know B original and B induced are going to be in the same direction, right? You need all this for this question. Okay, all of it. So I just gave you, all I did was just remind you of this problem solving tool, but now you should be saying, man, is this thing valuable? This thing's going to help me solve these problems. And it looks like according to this problem solving tool, I need to figure out what the heck B original is because I'm not going to be able to do anything else. And remember, when you make that statement, you hopefully you're remembering what we stated for the last question, which is that B is a vector. That was what took so long with the last question, right? Is all the directions. So hopefully that didn't disappear and you're not in this question and you've already forgot that magnetic field was direction, right? So if you're trying to find B original, that means you're looking for its direction and magnitude, right? That's what you're trying to figure out. And in this case, Dr. Asadi kind of helped us because he actually gave the way he ordered his questions for this test question, he actually ordered them in the way you should be solving it. So he's saying, hey, what's the B solenoid? Because the B solenoid is going to be the B original. Okay. So what is the equation for the solenoid? The magnetic field for the solenoid. And then also the direction. I need magnitude and direction of B because that's B original. Remember, that's why I'm doing it. I'm not randomly picking at anything. I literally cannot do anything else without this B original. I won't know what my change in flux is if I don't know the direction of B original because of this statement you just made down here about them being the opposite and same directions. Obviously, direction is crucial here. Okay, so that's the magnitude direction, right? It's going to be B mu, the current in the solenoid, right? And N over L, right? So this is going to be B. This is the magnitude of it. Okay. What do you notice about this equation? I'm going to write it over here, actually. This is something you should notice. This is something most students notice since Physics 1. It's something you all always point out to us. Always, always, always you point it out to us. It's an important thing, but it's the one thing that you're always able to recognize is what I'm trying to say. It's a good thing. It's super simple. Do you know mu? Well, it's mu naught. Do you know mu? It's a constant, right? You know it. Do you know n? Yep, 500. Do you know L? Yep, 10 centimeters. Do you know I? Uh-oh. Uh-oh. I don't see an I anywhere. Carl didn't forget to give it to you. Now what do we do? Remember, I see what you're saying. I see what you're saying. Sorry, I didn't see it kind of came down weird. Okay. So we're saying that, because of Ohm's law, right? Super, super important law, right? Is that we know that EMF is equal to IR, right? And right, if this is going to be the EMF of the solenoid, this is going to be the resistance of the, which is what that was. I should have labeled it the resistance of the solenoid, right? Then hold on, let me make sure. Oh, that's why I was thrown off here, because I was looking at I forgot to give you two numbers over here. But nothing that we needed right now. I just want to make sure that I write them down, because I don't want to get to that part and say, oh, I forgot to give you the number. We know the resistance of the hoop as well. That's going to be 2 ohms. And then we know the radius of the hoop. Sorry about that. Those, you didn't need any of those right now, as you can see, but I just realized I didn't give them to you. All right. So that's going to be, right, that's going to be the resistance in the solenoid. That's going to be the EMF in the solenoid. That's going to be the current in the solenoid. So if we solve this for the current in the solenoid, that's going to be the EMF of the solenoid over the resistance of the solenoid. Does that make sense? So now what do I do? Good. So we got to plug. Good job. Good job. Good job. That is the next step. Let's do that step. You're saying a lot of good things, but that's easier said than done, right? And if you don't realize that, you're about to see. But that was awesome. We said we got to put this into the right. We know this is the EMF. Oh, I didn't give it an S, but when I was describing it to you, I told you this was the EMF of the source, right? I went through the detail of it. And so, or the solenoid. And so we want to put that equation in here. Okay. So that's going to be right over RS. Okay, now what do I do? Nope, can't plug that into B yet. I mean, I could, but you're going to end up doing something later on that you should just get done now. Let me say that. Because I could plug this into B, but I'm trying to help you right now. Because regardless, you're going to have to do this, and you don't want to try to do this later on. So we want to put the 4 in down here as well. And the reason why is because, I mean, just like I said, you can put this in here, but then you're going to start dragging this R. I mean, it's going to get crazy. Do you see what I'm saying? Like you're going to put this into here, right? And then you're going to do something else with this equation next. We haven't even got to that point. And that, right, you're just going to be, it's going to end up as a mess. And so what you want to do is, when you put the 4 in here, you can see that this is 12 over 0 divided by 4 plus 0.0, oops, right, 0.8 t divided by 4. So we can see that when you do that math, right, we end up with 3 plus 0.02 t. And so that's a little, do you see how that's a little bit better to work with? Because essentially we want this current as a function of time, because the EMF is a function of time. Oh, thank you. Okay, so now I want to put this into this equation here. Let's just write these at the beginning. and then say that this is 3 plus 0.2. Gosh darn it, that fit that in. Yeah, just as long as everything checks out, I'll be posting it. Yes, yes, that's the plan. Man, I can't find space to fit this in right here. Fit. I just want you to see this all together. It's going to be 3 plus 0.2t. Okay. So that right there is the magnetic field equation for the solenoid. Does that make sense? As a function of time. Right, so maybe more appropriately, I might want to say, B of t, because that's what that is, right? That is a, right? Do you recognize that that's a function of time equation? It's going to be important here in 2 seconds if you don't, okay? So what is this equation telling us? It's telling us something. That's the magnetic field. So we got this part of the question done. The magnetic field of the solenoid, that's what that is. That is the equation. So that's the first answer. We have it. That is the S right there, right? What is it telling you? Yes, good job. It's telling us that B is changing, right? It's telling us, and can you tell me how it's telling us exactly how it's changing, right? What is it telling us? It's telling us how B is changing. And in what way is it telling us B is changing? What is it? I'm being vague here for a reason. Good job. It's telling us it's increasing. How do you know that? Good job. Because of this positive sign right there, right? If that was a subtraction sign there, what would that mean? That would mean decrease in the magnetic field, right? But because that's positive, that means an increase in the magnetic field, right? So it's telling us that the magnetic field is increasing. Why? Because we can see that the change is being added to it, right? The change isn't being subtracted from it. Does that make sense what I'm saying? That's very important. I know you understand me. So anyway, so that's the first question. So if magnetic field is increasing, then what does that mean? What else can you tell me? So this is the magnetic field for the solenoid. So we know that the magnetic field, well, first of all, keep in mind the current equation's telling us that the current's increasing, right? But then because of the current, we found out the magnetic field is increasing. And yes, that means if the magnetic field is increasing, there's an increase in flux, right? Because the magnetic field strength is increasing. Does that make sense? You keep asking me that and you're answering my question. Okay, so let's, right, now we got to look at that a little bit further, okay? So we know that flux is increasing, right? Because we know that, you know, in this equation, the change is being added. And if that's confusing to you, you know, you should recognize that whatever has the t value, the time value, sitting at whatever variable or whatever number has the t value sitting next to it, that's the value that's changing, right? The other value is what we call a constant, right? Does that make sense what I'm saying? This gets really mathy right now for a second. Okay, this problem, incredibly mathy. So, oh, I forgot to ask. I got so excited because you're telling me all these wonderful answers that are correct. We know the B of the solenoid is increasing, right? What direction is it? I forgot to ask you. I got so excited. We got the magnitude of it, and I forgot to ask you the direction because it's a vector. We need it. What is the magnitude of the magnetic field? I mean, the direction of the magnetic field for the solenoid. Good, it's up from the right-hand rule, right? If the current in the front is to the right and in the back it's to the left, all we do is we make sure our thumb is perpendicular to our fingers and we curl, right? We follow that, and I'll draw it up here, right? We follow the way that the current is, we curl our fingers in the direction of current, and our thumb, when you curl your direction, ends up pointing up, right? So the magnetic field for this current is pointed up, and it's up all the way through, right? Like it's all the way through. That's right, that's the B, right? It's up, and that's the B of the solenoid. So that's the direction, and this is the magnitude. The magnitude is increasing, right? And the direction is up. Cool. So now this is going to get really mathy. So what do we know here? So the next question is, you know, even if you didn't ask this question, it should be the next thing you're interested in, which is the induced EMF. So how do I write an equation for the induced EMF? And you don't have to give me the whole thing, but what, like, maybe I should be asking, like, what's the general equation? Like, what's the general equation for the induced EMF? It's E induced is equal to what? The change in flux over delta. Remember, this is the universe. This is the most fundamental equation. If this equation is not in your head, it needs to be there and live there rent free. Okay. All right. It's one of the most important equations in the universe, I would say. You need N for the coil. It's, you mean for the solenoid? No, that's the N, that's the sol, right? This is the magnetic field for the solenoid, right? So that means that this N is what? The number of turns in the what? I'm glad you asked that question. I didn't realize that that was confusing. Let's just be very careful about what you're saying right now, okay? I'm trying to help you. I would not, I would be very careful. I suppose we could put it in there. Let me say this. I could put it in there because you're saying, man, Carl, I want the N to be in here, but you're only concerned with an N if what? If what?
Okay. We're seeing this now, people. And
Like you're,
yeah, so
you're,
unfortunately we have a couple of
you're,
people who decided.
you're only concerned with N if it's a solenoid. And why is that? Why is N only important if it's a solenoid? Because if it's a straight wire or a hoop, well, first of all, for a straight wire, N is non-existent. But if it's just a hoop, just one coil, what is N equal to? Always, it doesn't matter. For a coil, N for a coil is always equal, not for a solenoid, but N for a coil always has the same number. What is it? No, you do. If you understand what turns are, I know you know this week. I know you do. If you understand turns, you know this. How many turns does one coil have? There, told you you knew the answer. I told you. Good job. So it's always one. Do you see what I'm saying? Why N's only important for solenoids? Because for a coil, it's one. I mean, you can go ahead and put it in there if you want to, but it's one. It's not even gonna, it disappears in the equation. Do you see what I'm saying? It's like not even there, essentially. But it is for solenoids. Does that make sense? And this over here is the end of the solenoid. I want to make sure you understand that. Like the solenoid. But, cool. But yeah, there's nothing wrong. You're right. There, like, you know, if we were trying to write the induced EMF for a solenoid, it would be equal to this. You're saying absolutely correct things. Oops. Yes, that's it. Okay. And this is the equation that we use for, you know, if we have like a system where we have like a solenoid over here and a solenoid over here, but this is the only solenoid attached to a battery, then we're going to have to get induction on this solenoid over here, right? And this is the equation we use. This would be the induced EMF on this solenoid over here. Does that make sense? So it's a very useful equation, but you got to know when to use it. So right now we just need this one. Cool. Does that make sense, everything I was explaining there? Okay, awesome. Okay, so this is the magnetic field. We know it's increasing because of positive sign. Okay, all these things. So what do I have to do next? How do I put these two equations together? It's done through the change in flux. So that's why this equation was so important, right? Because we know the change in flux can be a change in B, A cosine theta, a change in A, B cosine theta, or a change in theta. Remember, we talked about all this in the review. I can't talk about all this in detail right now, but you know that, you know, individually, 3 ways, because you could have combinations of these as well, but 3 ways individually is change in theta, change in A, change in B. And if there's no change in theta, we talked about this in the review, then essentially these equations turn into this. And here, is there any change in area? Is this the change in flux that we're looking at for this question right here? Or is it the change in B? Or is it both of them? Because it could be both. Good, just the B, right? And that's, we know by the equation. Good job, good job. That takes some concept, good job. So we know it's this one, change in B is going to be the change in flux. So how do I write that? How do I write that? This change in flux equation over here. How do I get the change in B essentially? Oh no, yeah. What I should be actually writing is, we know that's the change in flux, but I should be writing this, right? That was my bad. I forgot the delta T. It's changing at some rate, but yes, it's the B that's changing. If you're telling me to just put this equation in here, that's not correct. This is the magnetic field of a solenoid, and this is delta B. Those are not the same thing, right? It's like kinetic energy and the changes in kinetic energy, right? Those aren't the same thing. They have the same words, but they're not the same thing. So magnetic field, right, and delta B are not the same thing. They're related, very much so. So this is the spot that we're at right now. This is the hard part of the question. So don't, like, if you're sitting there going, man, I'm kind of confused, like you kind of should be, because this is confusing right now. I'll be honest with you. You got to have a pretty good idea of math to kind of know what to do here. It's pure math right now, okay? Don't worry about any physics. You're getting very, very, very close with saying slope, and you're like, slope, but slope of what? Like, talk to me, tell me stuff. Like, slope of what? Because you're right. It's definitely a slope. You don't have to think of it that way, but that will help probably. It definitely isn't going to hurt you, but it might not help you if you're like, I don't know what the hell does slope have to do with this. Well, yeah, okay, maybe that doesn't help, but you should know that slope is the rate of change, right? If you don't, like, let me explain it to you at least. I explained it to you, I believe, during the review, right? So here we know B is increasing, and it's increasing at some sort of rate, right? So the slope here is going to be the rate of change. That is correct. But it's one way to see it like this. It's another way to get the equation. So but that is correct. I think about that. I'm just giving you some time to think because this takes some thought. So I want you to take that time. I told you that doesn't help you, Wee. It doesn't help me for me to just give you the answer. I'll let you win this time because of the sake of time, okay? But if you have to do this on Dr. Maybe it's not this specific thing, but if you have to do something complicated on Dr. Asadi's test, your thought process can't be 5 minutes, give me the answer, okay? You have to be willing to spend more time on it and be okay with it. Okay, you have to, especially with his questions, because the logic I'm about to give you, I promise you, you would have never got this on your own. I'm not saying you're dumb. You know, I think you're one of the most incredibly both of you are incredibly intelligent. Okay, I'm not saying that. I'm just saying that this logic I'm about to give you, I'm telling you, you got to have a high level of math to think this way. Okay, because it's a high level of understanding. Okay. So this is what we know, all right? So the magnetic field of the solenoid, right? Any type of rate of change, first of all, and this is something you should kind of have an idea of if you've taken some sort of stats class or something like this, is that any type of rate of change always has some sort of constant, and the rate of change is always being added to some constant. If you've taken calculus, then you really know what I'm talking about right now. Okay, you know that those rate of changes, right, are essentially something that we call integrals, right, are some constant, right, added to the derivative. And the derivative is the rate of change. Now, I know I'm using calculus words here, but I want you to hear these things, and I want you to at least have heard them once in your life if you hadn't heard them before. Okay? So integrals let us look at the rate of change of a slope. Okay? And that slope is what we call an integral. Or I'm so sorry, a derivative. So sorry, an integral lets us look at the rate of change of an integral. Okay? And that's what we essentially have to do here. So what do we know? And integrals are some constant added to the derivative. That's what an integral is. Okay? And so we can actually see it. Again, we're not doing any calculus here. That's what's so beautiful about algebra. And believe it or not, even the calculus students, their trouble is not the calculus, it's the algebra. And right now we're doing the algebra because the algebra is really what gets the business done for you. Okay, you can sit there and write a derivative all day. If you can't solve that derivative, which is going to take, or integral or whatever, if you can't solve that thing, which is going to take algebra, then who cares if you can write the integral solving the thing. And then look at this. So this right here is going to represent our constant. And then it's going to be added to some kind of change, right? Which is this, which is going to be this, 0.2t, right? So this right here is the rate of change. this right here is the constant. Does that make sense what I'm saying right now? And so we, for the change in flux, we're only concerned with the rate of change. We are not concerned with the constant part. Does that make sense? We're only concerned with the rate of change. So that means that only this part of the equation goes in here. Does that make sense? Awesome. So let's do that. So it's going to be mu n over L. That delta t is still there. You're going to see something that's going to happen again. We're doing calculus, but with algebra, believe it or not. It's so cool. I love Dr. Sadi because he does this stuff. Like, anyway, it's a really cool thing. Like, it's like, man, you can do calculus with algebra. You don't need to take a calculus class. You can still do calculus. Okay, so this is what we have. And this t right here, we write it as t, but it's essentially some delta t, right? It's how time's changing, right? But it's going to be some t, just like this t down here is going to be. These t's and t's, and maybe I should write it more like this. So I want to keep that as t. Right? Is that this delta t we can essentially just write as t, because that's going to be some, some rate of change in time, which is these two t's are going to match. And then just like you would see in algebra, no joke, okay? These, exactly, good job, my man, is that these two t's are going to cancel, right? And again, if you haven't taken calculus, that's okay. But if you have, you're probably like, oh man, I remember all this stuff now. I remember doing all this stuff. Right? So essentially we have this, right? We have this equation. I'll just write 0.2 like that. There we go. So that is our rate of change in flux. Does that make sense? This is our equation for it. Does that make sense? Oh, no. I patched it off. There we go. Okay, so now what do we want to do is, since the induced EMF is equal to the change in flux, what does that mean? I need to say that the E induced is now equal to what? Tell me. Oh, crap. I just remembered. I forgot this. I left this A out. I'm so sorry. That needs to go there. That A didn't disappear, okay? We were just dealing with the rate of, I'm so sorry I forgot to write that A because I was trying to teach you calculus here. That A is there. I'm so sorry. Because it's right, it's the induced EMF, or the rate of change in flux, is change in B over change in T times A. So that A is still there. I'm so sorry. Is that cool? Does that make sense what I'm saying? That this area, that area from this equation right there, I kind of forgot to write it here and here, but it does go there. Cool. Does that make sense what I'm saying? Like, this is that area. Hopefully that makes sense. And so the induced EMF is going to be, essentially all these numbers, right, times that 0.2. Does that make sense? And you should know area, because this is the induced EMF in the hoop, So what's the area of the hoop? What is the area of the hoop? It's just a circle, right? So 2 pi r, right? And he gave you the radius of the circle. I mean, of the hoop. So just make sure you know that. Okay. So that's the induced EMF. What's I induced? We're almost done. Oh. Thank you. I forgot to write the r squared. Thank you so much. My bad. Okay. Where this is the radius of the hoop. So what's I induced? Oh. I'm doing too much now, aren't I? Look, I can't help but write the pi. The 2. Is it pi r squared? I thought it's 2 pi r squared. Are you sure? I feel like the area of the hoop. Okay. I don't know why I thought it was 2 pi, but anyway, what's the induced EMF? That's still the question at hand here. But thank you for that correction because that needed to be corrected. What is the I induced? It's really easy. That's why I'm asking. You should just be able to it's super simple. Based on, we essentially got the answer. Exactly. There you go. It's just Ohm's law again, right? It's just Ohm's law again. Let me slide this over.
Are you good? Okay. And then yeah, Coolidge, do you know you for sure will be coming? Maybe so you can, make sure things are going well.
So that's going to be I, right? I showed you Ohm's law already, right? You should know Ohm's law. We did it over here. We're just using it again where, the EMF is equal to I times R, not of the solenoid now, but of the hoop. So that means the current of the hoop, right, is going to be equal to the EMF of the hoop, which is what this is, right, that we just got, over the resistance of the hoop, which he gave us that number. So that means that current is going to be equal to mu NA over L times 0.2 all over R. Cool? And that's the induced I. Now, what direction is that? So that's the value, that's the magnitude of the induced I. Where again, this A is still pi R squared of the hoop area. But what's the direction of the current in the hoop? We said flux is increasing, right? So if flux is increasing, what direction should the induced magnetic field be for the hoop? Because that's how we got to do this, right? And then do the right hand rule. So if the magnetic field of the solenoid is B original, right? And that means, and that's pointing upward. Good job. That means B induced needs to be in the opposite direction because flux is increasing. So you want to put your thumb downward because B of the solenoid, remember, is acting as B original. This is B original, the solenoid. And since we're trying to find the current in the hoop here, and flux is increasing, we know the induced magnetic field for the hoop is going to be downward, be induced. Right? That's going to be downward. And so by using the right hand rule, which is putting our thumb in the direction of B and curling our fingers, right, we see that the current in the front is to the left and to the back, and the back is to the right. Right? So we can see it's going in the opposite direction than the current in the solenoid, right? Because the current in the solenoid in front, it's to the right. But for the hoop in front, it's to the left, right? See that? To the left. Does that make sense? Awesome. Okay, so that's the end of that question. That's it. We didn't make it to the final one. It's really not that hard. It's very, 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 very straightforward. In fact, I'm just going to do it here real quick. It's that quick. It's such an easy question, okay? So he says an RLC circuit with the resistance of 4 ohms, or yes, and inductor with 4 microhenries and a capacitor with capacitance of 5 microfarads. And it operates at a resonance frequency. Okay, so it operates if you don't realize it, that's a given. Okay, operates at resonance frequency. And the current through the inductor I sine omega t. So the current in inductor. Okay, a little bit clearer. Okay, you know it operates at resonance. Okay, and the I in here, he also says that this I in the current is equal to 3 amps. So he wants to know, find the total current through the resistor and the capacitor. So let's write that a little different. He wants to know IR and IC. Okay. As a function of time, right? So maybe I should write it like this. I'm writing this. He does not put this in the test. I'm doing this for you to show you like how to change it. So since he's asking for current as a function of time, I know he's looking for these things. Okay. So he wants to know the current across the resistor and across the capacitor. As a function of time, he wants to know the voltage in the resistor, the voltage in the inductor, and the voltage in the capacitor. He wants to know all these. I know this sounds like a lot, but it's so easy to get. And then he wants to know the EMF of the source. EMF of the source as a function of time. Should have known that. And then draw a phasor diagram for the circuit and discuss the results. So that last one, hopefully I'll be able to get through all of that. I'll at least get the equations. But the phasor diagram I might not be able to get to here because I didn't see that till the very end, and that might take a second. But if I have time, I'll do it. So I'm not going to ask you any questions. I'm just going to tell you the answer here. So what do we know? Something you should already have in your head from the review. We were given the current in the inductor. But what you should know from the review is we said that these RLC circuits, they're in series. They're series circuits. We're never dealing with, right? We never ever talked about parallel circuits for RLC, and we never are going to. All we've talked about is series. So you shouldn't even be thinking another way. You shouldn't be thinking, are these parallel or is it? No, the chapter was titled series circuits. Okay, RLC series circuits as part of the title of the chapter. So because everything's in series, you know, if you know the current in the inductor, that means you know the current in the resistor and capacitor. Do you remember that from the review? Remember saying that from the review? You said it a ton. Okay, and this right here, right, is IMAX. So that means that this right here is going to be, you can like blindly write these because they should all match. The current in the capacitor, resistor, and inductor should all have the same equation, right? And the I, which is I max, is going to be represented by that number that he gave us over here. Does that make sense what I'm saying? It's that simple. Was that confusing in any way? Because you should be able to just blow through this answer very quickly. So that's the first, like, we're literally, that's the answer to that first part of the question. We literally just copied what he gave us because it's a concept. It's not a math thing. It's not like, oh man, how do I solve this? No, it's a concept. You know that the equation for the current needs to look identical for the inductor, resistor, and capacitor because it's a series circuit. If it wasn't, it would be different. But because it is, that's the idea, okay? What's the next thing that we know or we're being asked? The potential in the resistor, inductor, and capacitor, right? Well, again, from the review, I'm going to be referring to that a lot. So if you didn't watch the review or weren't there for the review, but obviously I posted the video for it. So watch that so that you know what I'm talking about because I'm doing a very abbreviated version here. But what you should know, and these are also as a function of time, I should have written that, is that we know for the resistor, potential and current are in phase, which means there's no leading or lagging. That's what we know. Always. This is always true. It doesn't matter what the situation is. That's always true. Okay. We know for the inductor that the potential leads the current, and we know for the capacitor, the current leads the potential. Okay, we talked about this in the review. If you don't know this, you need to know this, otherwise you won't be able to answer this question. Okay, so since R and V are in phase, that means that there shouldn't be any phase difference representation in the equation. And remember, the way that we do a phase difference representation in the equation is that we either put a positive phi or a negative phi. Actually, what we really write is positive pi over 2, because this is, you can write any phase difference in terms of phi, but because of concept, we know that the phi is, in this situation, is pi over 2, because we know that these things are always out of phase by 90 degrees, which is, in terms of radians, pi over 2. So we know that these pi over 2, right, is going to be the phase difference for both the inductor and capacitor. Again, I talked about this in the review. I shouldn't be explaining this right now. I'm trying to do this fast. Okay, so if nothing's leading or lagging, you're not going to have any adding of pi over 2 or subtracting of pi over 2, which is what we see in the resistor. So it should just be very generically written as V max, okay, and then sine theta. Since they're in phase, again, watch the review if you're not too sure, but since they're in phase, or if you don't understand this, they're both sine graphs, and then omega t, and we're done. That's the equation for this. That is literally the answer. What you should, because based off the givens that he gave us, right? He didn't give us the potential in the resistor, but we know what it is. So it's going to be, sorry, this V max is going to be equal to I times R. Okay. And we know the current, right? This is the current equation right here. Or in this case, if we're looking, if it's V max, and this is actually going to be I max, sorry about that. And then R. So I max, which is right here. You know that number. Okay, it's right there. Right, I'm flashing it at you up there in the top right. Okay, that's I max. And then R, you also know it's up at the very, very top. This thing would stop giving me an eraser. Right, and I'm flashing at you right now, top left. That's the resistance. So that's the R that goes in there, right? And the I max. So that's going to be the number for V max, okay? You got to state this on the test. You can't leave that out because you don't have V max here, but you have I and R. So that's what you need to have here. Does that make sense what I'm saying right now? Hopefully it does. And the next thing, right, we know the V in the inductor, right, is going to be VL, right? So that's the potential in the inductor specifically. And then again, we use the sine function here. If you don't understand why, watch the review. And then here, right, we said in the inductor, potential leads the current. So that means this needs to be omega t plus pi over 2. Okay, because it's leading. Plus means lead. Okay, I actually didn't write that there. But this means lead. This means lag. Okay. Positive means lead, negative means lag. And so potential leads current. So that means we want a positive sign here. For the capacitor, we know that potential, we know that potential lags current. I have it written there as current leads potential because that's another way to say it. Current leads potential, or you can say it in another way, which is potential lags current. Okay, so potential lags current, the way we want to write the potential equation for the capacitor would be just a minus pi over 2, because that's going to represent a lagging. Okay, so these are the answers. What you are for the potential as a function of time, it really is that easy. And what you should know is that VL, right, what's that going to be equal to? I times XL. And VC is going to be equal to what? I times XC. Okay. So what's XC and XL? Those are the what we call the reactants, right? XC is equal to 1 over omega times C. Yes. And the XL is equal to omega times L. Is that correct? Make sure. For some reason I feel like I. Correctly here, but yes. Okay. So this is what we know. Now, we know this thing is operating at resonance frequency. Okay, that's kind of important to know here. And the reason why that's important to know is that we know that that XL and XC, they should be equal to each other at resonance frequency. That's it's something that it's a concept. It's a concept, okay? And so because of that, right, we can really solve for any one of these numbers and they're going to be the same. But if you want to actually solve for one of these numbers, which you should want to, again, Dr. Asadi will just accept these equations that I have sitting in front of you, but you got to make sure you establish something. So C and L because they were given to you in these equations, in these reactance equations, but you don't know omega, but you actually do, because since this thing operates at resonance frequency, which is what we set up here at the top, right? that means that omega, you do know omega. Omega is equal to 1 over the square root of L times C. And you have L, you have the inductance, right? And you have the capacitance. Those were two givens. So you have omega. Do you see what I'm saying there? And since this thing's operating at resonance frequency, this omega naught, we can write those as omega naughts because those are actually resonance frequency omegas. Does that make sense what I'm saying? Hopefully it does. And so, so that's how you're going to get, right? This XL and XC. That's how you get these, the equations for those. Okay. So once those, so that what we got here sitting in front of you right now is we got the current as a function of time equations, and we got the potential as a function of time equations. Those are the first two things he asked us for in this question. The last thing he asked us for was the induced or not the induced EMF, the EMF of the system. Okay, so where he wanted the EMF of the source as a function of time is really what he was asking for. So how do we write that? So we know that the EMF as a function of time, right, is written just like the potential equations, right? It's going to have some sort of amplitude, right? And that amplitude is going to be E max, right? The max EMF of the source, right? And then it's going to have some sort of sine function. Again, we talked about this in the review. And then there's going to be, some omega t, and then it's either going to be plus, right? There's going to be some phase shift, right? Which we called phi. But that phase shift, this phase shift is not pi over 2. Okay, that's we have to solve for that phase shift, right? And so we'll do that here. So what's EM? Well, E max, right? If you remember series circuits, right? E is equal to if you remember from chapter 18 doing the circuits, you remember that the loop rule where the EMF, right, was equal to the amount of potential, right, in the system. So the total EMF was equal to the loss of potential in the system. If you don't remember that, I'm reminding you. Okay. So we know that the total EMF of the system is equal to the potential of the resistor squared. Again, I explained all this during the review, times the potential of the inductor minus the potential of the capacitor squared. Okay, so that's going to be this number right here. Okay, that's going to be the equation for that. This phi, right, we're going to use that tangent theta that I talked, or tangent phi that I talked about yesterday in the review, right, where this is VL minus VC over VR. And again, remember the VL is equal to XL times R, right? The VC is equal to XC times R, and the VR is equal to the oops, these are supposed to be I's, not R's. I didn't make that same mistake. Hold on, I have to go check now. Why is this not writing? We'll have to make sure that I didn't make that mistake. Oh no, I wrote I's. Okay, good. I was just making that mistake over here. Okay, so these are all right. Current, it's just Ohm's law, right? So that's what this, these VRs, VLs, VCs that I have written in these equations over here. Remember, this is what their numbers are equal to, and I showed you how to solve for those XLs and XCs. Okay, and then in order to get phi, right, we just do the inverse of tangent. VL minus VC over VR, and that's going to be this remember, we're trying to fill in this equation up here, right? So this phi is going to be that phi in there. Okay. So that's the answer. I'm out of time now. I got to run to that other SI. Okay. But, he wants you to draw a phasor diagram here. I don't have time to do that right now. But if you have questions about that, you can send me an email. Thank you so much. I really do got to run. I took literally all my time. But you all have done wonderful. If you have any questions about this review or any questions we've done here, please send me an email. But other than that, have a good night. And please, if you have questions, send me emails. I can't stress that enough. Or Dr. Sadi. So, all right. Have a good night. I'll talk to you all soon. Bye.